Hey everyone, it's Dr. Garner here. In this video we're going to learn a bit about light. So the different types of light that exist are arranged according to the electromagnetic spectrum that we're seeing here on this slide. So the electromagnetic spectrum classifies these different types of light based on how they interact with matter. And what we've done here is we've arranged them in the spectrum in order of according to their wavelength and frequency. So over here on the right we have long wavelengths and low frequencies. Over here on the left, we have shorter wavelengths and higher frequencies. And each of these different regions of the electromagnetic spectrum describes the way in which light within that region interacts with matter. For example, radio waves tend to excite the spins of nuclei. Microwaves tend to cause molecules to rotate. Infrared light tends to cause molecules to vibrate. Visible and ultraviolet light tends to excite electrons to higher energy levels, and ultraviolet light can also cause some electrons to be lost from atoms. X-rays tend to cause inner shell electrons or core electrons to be lost from atoms. Gamma rays tend to do the same thing, but tend to come from different sources, so different sources of light. So each of these regions is named based on how it interacts with matter. So we can think of the behavior of light in many ways like a wave. So light exists as a series of oscillating electric and magnetic fields. So we have a magnetic field oscillating in one direction, and then perpendicular to that we have a magnetic field, an electric field oscillating in that other direction perpendicular to that. And then we have the light wave propagating in some direction here. And we can describe, according to that wave, we can describe a wavelength and a frequency associated with the wave. So like with any wave, a wavelength is the distance covered by one cycle of the wave. So you can think of this as the distance between two peaks. And you'll often see this abbreviated with this lowercase Greek letter lambda. So lambda describes the wavelength of light, which again is just the distance covered by a cycle of a wave. So you would measure this in units of distance, in units of meters. We can also think about the frequency of a wave of light. So frequency, we abbreviate that with this lowercase Greek letter nu. And the frequency of a light wave describe how many cycles of a wave pass a given location in space per unit time. So in other words, how many peaks pass a certain location per second. And as with any wave, if you multiply the wavelength times the frequency of the wave, that's going to give you the speed at which the wave is propagating. And in the case of light, the speed of light is a fixed constant for the universe. So the speed of light is always this value that we're showing here, which is approximately equal to 3 times 10 to the 8th meters per second. So the speed of light is a fixed quantity, 3.0 times 10 to the 8th meters per second, at least in a vacuum. And it equals our wavelength times our frequency of the light. All right, so light behaves in many ways like a wave, but there are other properties of light that are not consistent with wave-like behavior. And we're just noting a couple of these here. You don't really need to know the specifics of these. But blackbody radiation is one example of that, and that's what's being shown here on this slide. So blackbody radiation is the light that's given off by hot objects. So like this hot coil on a stove that's glowing red, it's giving off some light. The type of light, the wavelengths of light that are being emitted by the stove are not consistent with wave-like behavior of light. You wouldn't be able to predict this phenomenon based on light behaving solely as a wave. And these phenomena that we're describing here, they exist because matter can only lose energy in discrete quantities. So in other words, matter can't lose energy in continuous amounts. So matter can only emit or absorb energy in discrete units, or discrete quantities. And these units of energy that matter can lose in the form of light, these are known as photons. So you can think of a photon as being sort of like a particle of light. Right, so light has this wave-like behavior, but it also has a particle-like behavior. So it kind of exists in both ways simultaneously. And these particles of light, they have a certain amount of energy associated with them. And we have this equation here that we can use to describe the energy that's present in a pulse of light. So E here represents the energy present in the pulse of light, and it equals N times H times nu. So N here is the number of photons that's in the pulse of light, so that's an integer number, it's the number of photons, times this constant H, which is known as Planck's constant, and has a value of 6.626 times 10 to the negative 34 joules times seconds, and then times nu, which we saw on the last slide represents the frequency of the light. So you can use this equation to relate the energy of light to its frequency. If we put these two equations together, we can see how wavelength, frequency, and energy are all related to each other. So as the wavelength of light increases, its frequency is going to decrease. So as we saw a couple of slides ago, the speed of light is equal to the wavelength of light times its frequency. So in other words, this product of wavelength times frequency, it equals a constant. So this product equals a fixed value of c. So if our wavelength is increasing, that means this value here, lambda, is going up. In order for this product, therefore, to still equal this constant c, the other value in the product, the frequency, must be going down. So wavelength and frequency are inversely related. As one goes up, the other has to go down in order for this product to still equal c. We see a different relationship between frequency and energy. As frequency increases, the energy of a photon also increases. So these are directly related, so they're directly proportional to each other. And again, we saw in that last slide that these are related by this equation E equals nh nu. So the energy in the pulse of light is represented by E, and our frequency is represented by this lowercase nu. So as nu increases, as frequency increases, then the value of E is going to increase as well. So they're directly related to each other. All right, let's try out a practice problem here. Again, I would suggest pausing this and working through it on your own first, and then taking a look at the solution. All right, so the wave that we're being shown here, so we're being shown a diagram of a wave, and we're being asked what color it is. And we're given this color wheel over here that gives us the different regions of the visible region of the electromagnetic spectrum, and it gives us these values in nanometers. These represent the wavelengths of light that correspond to each color of the visible region of the electromagnetic spectrum. And we're also being given, again, this diagram of a wave over here, and we're being shown this distance here. So of course what we need to do is we need to figure out what the wavelength of this light is, and then we need to convert it into units of nanometers so that we can compare it to the values that were given over here in the color wheel. All right, remember that a wavelength describes the distance between two peaks in a wave, or more generally, it describes the distance covered by one cycle of the wave. So that might be the distance between two peaks, might be the distance between two troughs, it might also be the distance between two rising midpoints. So that's what we have here. This is one cycle of the wave, one up and down and back up again. So that's one cycle, one more cycle, and then a third cycle here. So this distance that we're seeing represented in this diagram represents 3 cycles, or 3 times the wavelength of this light. So if I want to find this value of wavelength, this value of lambda here, I can take the distance that I'm given, the 1.596 times 10 to the negative 6 meters, and divide it by 3, right, since there are 3 cycles of the wave here. My value of lambda is going to come out to be 5.32 times 10 to the negative 7 meters. Again, that's in a different set of units than what I'm being given here in this color wheel. So it would be helpful if I could convert these units in meters back into units of nanometers so that I can compare it to what I'm given here. In the last lecture, we saw that nanometers are equal to 10 to the negative 9th meters. So 1 nanometer is equal to 10 to the negative 9th meters. So I can multiply by that conversion factor. I can take my value in meters and multiply by 1 nanometer per 10 to the negative 9th meters. If I do that, these units of meters are going to cancel out, and I'm going to be left with units of nanometers in my answer. So it's going to give me 532 nanometers. Now all I need to do is just find that value and see where it falls on this color wheel. So that's somewhere between 490 and 560. So it looks as though this wave of light corresponds to the green region of the electromagnetic spectrum. All right, let's try out another problem. So again, I would suggest pausing the video, and taking a moment to think about this one on your own, and then taking a look at the solution. All right, so which photon would release the most energy? And we're given some choices here that correspond to different regions of the visible portion of the electromagnetic spectrum. And we're also being given a color wheel here that tells us the different wavelengths associated with the different regions of the spectrum. So it looks like, according to this wheel, it looks like red has the longest wavelengths, violet has the shortest wavelengths, and everything else is kind of somewhere in between. So we can pretty much narrow this down to either A or B at this point. All right, we're trying to find the region that has the highest energy. And as we know, energy is related to frequency through this equation E equals nh nu. So if we want a high energy, if we want this value to be big, we also want a high frequency. We want frequency to be large as well, since those are directly related to each other. So if this goes up, that has to go up as well. All right, so we know that we're looking for the highest frequency light, so now we need to think about how that relates to wavelength. So frequency and wavelength are related by the equation c equals lambda nu. So c, the speed of light, equals our wavelength times the frequency of the light. So in this case, if we're looking for a high frequency, we want this value to be really big, that means that the wavelength here is going to have to be really small in order for that product to equal this constant c. So if we want a high frequency, that means that we need a low wavelength, a short wavelength. All right, so if we're looking for a high energy, it means we're looking for a short wavelength. So it looks like the violet region with its shorter wavelengths is going to be the photon that we're looking for here that has the higher energy. So our answer here is going to be V. All right, well, I'll stop there for this video. I'll see you guys in the next one.